going to do, instead of reading a long summary of the talk, I'm going to read the last line. This is a perspective on software development that will change how you view code. Promise. Let's all welcome Adam Tornhill, Code Red, the business impact of code quality. Welcome, Adam. Welcome to Athens.
Thank you. Good afternoon, everyone. Can you hear me well? Perfect. So, welcome to this talk where we will dive into the business impact of code quality. And we're going to start from the perspective of technical debt. So technical debt is something that I like to think that most of you are familiar with. And as an organization, we take on technical debt for different reasons. Maybe we try to compromise quality so that we can deliver a feature quicker. Ever heard that one? Yeah. Or maybe our understanding of the business problem evolves so that our design is no longer a good fit. Or perhaps, just perhaps, our design wasn't a good fit to start with. So while the root causes might be different, at the end of the day, the end result is the same. We end up with code that's more expensive to maintain than it has to be. And this is the definition of technical debt that we're going to use for the purpose of this talk. Now, over the past 5 years, there has been some very fascinating research on technical debt and its consequences. And depending on which paper you look at, you will find that the numbers vary. And they vary somewhere between 23 to 42%. What do I mean by that? It means that companies today are wasting up to 42% of their developers' time dealing with technical debt and bad code in general. 42% waste. Does that sound like a good deal to you? It's disastrous. So as a thought experiment, let's consider what this actually means. It means that if I have an organization with 100 developers, and with a 42% waste, I would get the equivalent of just 58 people out of that. Right? That's a massive waste. However, the bad news are that even that number is overly optimistic because with 100 developers, there's a significant coordination and communication overhead, right? So you pay that additional price as well. So the actual waste is probably much, much larger than what's indicated in the research papers. Unfortunately, technical debt doesn't just stop at the financial impact. There's also a severe impact on the security of our applications. So many significant code smells, we're going to cover some of these later in this talk, they also have a strong correlation to security vulnerabilities. So technical debt impacts both the financial side and the security space of our products. Now, given what I just told you, you would expect technical debt to be really, really high on any decision maker's agenda, right? It's the first thing we start to look at in the morning, isn't it? How can we reduce that waste? No, of course not. In fact, the research paints a pretty depressing picture here. It turns out that what we see in research is that most developers are actually forced to introduce even more technical debt as companies keep trading their future well-being, a healthy code base, for the lure of quick fixes and new features. So why is this happening? Why are we making these trade-offs? I like to think that there's a difference in feedback timing here. Think about it for a moment. What happens when we implement a new feature? What happens is that we get an immediate reward, right? We get a happy user. Maybe we win a new business contract, right? Or maybe we increase our NPS score. All these good things that are immediate. However, when we take on technical debt, the consequences are long-term. And once we notice the symptoms, it might already be too late. And these differences in feedback timing, they are like an open invitation to a decision-making bias known as hyperbolic discounting. So has anyone heard about hyperbolic discounting before? Only a couple of you, that's good. I get something new for you. Perfect. So hyperbolic discounting, this is when we as humans make decisions today that our future selves are going to regret. Right? So think about this when you go to the after party this evening, right? That's a typical example on hyperbolic discounting. Hyperbolic discounting is used in psychology when studying addiction. It's also, coincidentally, the best description I have found on why companies fail to manage technical debt. Because just like the addict, we trade our future or maintainable code base for the lure and quick fixes of the next new feature. So, in the words of Mel Conway, it kind of seems that there's never enough time to do something right, but there's always enough time to do things over and over again. So how can we fight this bias? How can we fight hyperbolic discounting? How can we make a better job around managing technical debt? During my almost 3 decades in the software industry, every single person that I ever talked about, that I'd ever discussed technical debt and code quality with, everyone kind of agreed that code quality is important. Everyone knows that, right? But I like to claim that it knows within quotation marks. Because until today, no one ever had any data to support that statement. And consequently, code quality remains a very abstract concept that doesn't really mean anything to the decision maker. It also means that code quality remains largely undervalued at the business level, right? It's something very abstract that we cannot really touch or see. So the first way of fighting hyperbolic discounting is to make it visible. So let's see how we can visualize code quality. This is an approach called code health. It's going to show up in a couple of seconds, I hope. Otherwise, it will be a short presentation. So code health is a concept I've been working on for the past 7 years. And you see an example to your left. I'm going to go through the details later of that visualization so that you know what you see. For now, let's just focus on the different colors here. What you do with code health is basically that you categorize every single module with code into one of 3 different categories. So we have the green category. That's green code. That's healthy code. That's where you want most of your software to be. Because healthy code means that you, as a developer, can easily pick up that code, you will be able to understand it, and you can make modifications to it safely with low risk. Then you have yellow code, and this is where we need to start to be careful because this is the warning space. It means that the code has started to accumulate some technical debt, and unless we're careful, we might end up in the red category. And red code is code with severe maintenance issues, and once you're there, it's going to be really expensive to reverse that trend. I'm going to give you some specific examples. So to determine the different categories, we need to look at many different attributes of our software. So the code health concept that I'm using in the study that I'm going to present to you looks at 25 different factors. And I'm just going to give you some examples very briefly on what those factors are so you can relate it to something specific. One thing we look at is at the module level, is that module or class cohesive? Meaning, does it implement a single responsibility? Because low cohesion is one of the most cost-driving problems in software today. And that's low cohesion is simply when you stuff multiple responsibilities into the same module, right? So now the code is really hard to understand because you need to understand all these different business rules. It also exposes you to things like unexpected feature interactions, which are some of the worst bugs you can ever have, right? But of course, there are different degrees in code smell hell, and we can always make things worse. And one way of making a class with low cohesion worse is by turning it into a brain class. So this is a class that not only is low in cohesion, but it's also really, really large and has a lot of complicated logic in it. And so on. There are different function level smells, things like a brain method. You might know that one as a gut function. So if you ever programmed, you have come across brain methods. It's this method that's really, really long. It's very complicated, it has lots of logic in it, lots of different decisions. And it tends to be very central to the module, meaning that each time you want to modify something in that module, you end up in the brain method, and over time it becomes more and more complicated. Anyone ever seen that? Yeah, you're in good company. And then of course classics like copy-paste programming and so on. So these are the factors we scan, and then we have algorithms that can simply categorize them into one of these 3 different categories. Now, using this concept, we can actually visualize the code health of any code base. And I want to show you an example here of how quick it is to determine where the most severe technical debt is. So this is a visualization of Ethereum on open source blockchain implementation that some of you might be familiar with. Let me walk you through the visualization so that you know what you see. First of all, have a look at these different circles that I'm hovering over right now. Each one of those circles represents a subsystem or a high-level component. So if this was one of your code bases, you would recognize the names of those circles as some business-critical component, some architectural element. It's also an interactive visualization, so I can click and zoom in on any part that I'm interested in. And then I reveal the kind of subfolders inside that service or component, and once I get to the lowest level, I see that each file with source code is visualized as a circle. And you see that the circles, they have different size, right? So size just reflects the number of lines of code. So the larger our module, the larger the radius of the circle. The important thing here is the color, which signals how healthy that code is, right? So here we see an example on some red code that we know is problematic, and 2 instances of green code. In general, I'm a big fan of visualizations, because visualizations, they do tap into one of the most powerful pattern detectors that we have in the known universe, the human brain. And by visualizing code quality, we can quickly see where the strong and weak parts are in our code base. And I want to give you some examples. So here on screen, you see 2 different code bases. The one to the left is React, a UI library from Facebook that some of you might actually be using. So how many, let's do a quick poll on that. How many of you are using React as part of your products today? So it's like, I would like to say 1/5 of you maybe. It's a very popular library. And using this visualization, we can quickly see that most of the code in React seems to be yellow and green, so it seems to be pretty okay. But there is definitely a warning sign because we have this cluster of red modules, right, in something called React Reconciler. So if this is one of my products, then this is important information to me, because this information, this lack of code quality in React Reconciler is going to constrain what I can do with the code base and the business. The code base to the right here provides an interesting contrast. This is a code base from Microsoft called Core CLR, the Common Language Runtime. So those of you who run Windows laptops, you might have this software at your laptop right now. And hopefully we can get back to visualization soon, because I'd like to point out an interesting contrast. Here we go. So if you look at the Core CLR code base, you see that this one has a very different pattern compared to React, right? We have this band of red code, right? It looks like a, like a bacteria culture gone mad, right? A lot of red code. Add to that fact that the code base is more than 8 million lines of code, and you know that this is going to be really challenging to work with, right? Towards the end of this session, I'm going to show you some technique on how to prioritize a starting point for improvements, even in code bases like that. But before we go there, we need to take a step back and see how can we actually quantify the business impact of code quality. Because just knowing that code is red or green, I mean, we want that to be something more than just a vanity metric. It has to mean something to us as a business. And last year, me and a colleague set out with the task of solving this to relate code quality to a business impact. And the way we did it, by the way, you have the link here to the formal research paper if you want to read up on it, because everything I'm going to tell you has been peer reviewed, was presented at the International Conference on Technical Debt, an academic conference. And everything I'm going to show you is statistically significant, meaning that it's a real signal, not just random noise. The way we did this was that we collected data from 49 different companies, so they gave us access to their code bases. And we measured the code health of every single module that they had. So there were like 40,000 modules, something like that, several million lines of code. What we also did was that we connected to their Jira data and to their version control system. And by doing that, we could calculate the time in development for every single feature. And we could relate that down to the file level. I'm going to show you how in a minute. What we could also do was that we could extract data about the type of work that they do. So were they doing new features or were there more bug fixes in specific parts of the code? So we basically imagine a large data set where every single row is a specific module with the known code health, red, yellow, or green, the time spent in development on average, and the number of defects in that module. And using that data, we could finally start to answer this question. And before I reveal the results, I just want to show you how we measure time in development, because it's such an important metric. So I want to make sure that I manage to explain what you see. And I promise you, this will be my most technical slide. I'm going to try to keep it high level. So when measuring time in development, what we wanted to do was to avoid to put some administrative burden upon the programmers and have them report them, right? So what we did instead was that we pieced it together by combining Jira data and version control data. So here's how it works. Let's say that you as a developer, you start working on a task, so you move it to an in-progress state in Jira. The moment you do that, we start the clock. Then you write the code, and at some time you commit that code. That's where we stop the clock. So if this was all you had to do on that task, then the time in development is the time between the task moving to in progress until the first commit. However, very often, changes are more complicated than that. So if you do multiple commits, then we simply continue to calculate the time between commits and we sum it up. So at the end, we have a pretty good estimate on what's the cycle time for implementing every single feature down at the file level. Did I manage to explain that? Some of you are nodding. That's a very good sign. Thank you. So let's look at the results. Does code quality matter? And if yes, how much? The first thing we looked at was this. What's the time to market? What's the time in development? And it turns out that with green code, you can be more than twice as quick with implementing a feature as a similar feature in red code. And this is really, really important to a business, because what this means is that if we, as a company, let's say that we have red code, if we can implement a specific business capability in 2.5 months, our competitors can get the same thing in less than 1 month if they have green code. It's going to be really, really hard for us to keep up. However, I have to admit that this didn't really surprise me, given what I would have guessed after working with software for all those years. What did surprise me was the next thing we looked at. What we looked at here, a cliffhanger. So let me start by talking, and then the results will show up very soon. So what we started to look at here was uncertainty. So instead of looking at averages, like what's the average time it takes to implement a feature, we looked at the variation, like what's the maximum time it takes to implement a feature, depending on if your code is green or red. And as you see here in the graph, here's a very dramatic difference. And the thing is that with green code, it seems to be very predictable, that when implementing a feature, the variation is very, very low. It's very close to the average time, meaning that work in green code seems to be very predictable. And predictability is something that's in general pretty good. For red code, the opposite seems to be true. So in red code, implementing a feature, there's a huge variation in the task completion time. It can actually take almost an order of magnitude longer to implement a feature in red code, a factor of 9. So what does this mean? To me, it means uncertainty. Red code comes with uncertainty. And uncertainty, let me assure you of this, is something that no one, really no one likes in the software industry. I'm currently working as a CTO, and I strongly dislike uncertainty, because uncertainty makes me look bad, right? Let's say I promise you a new feature that, hey, you can have this feature next month. But if we have red code and that feature takes 9 months, that's going to come back and haunt me, right? I'm going to break my promise. I couldn't do anything because the code was red. If I instead take on my developer hat, I also dislike uncertainty, because uncertainty is what's causing me stress, overtime, and missed deadlines. Now, the last thing I want to show you with the business impact of code quality is the link to correctness. So I already mentioned earlier that technical debt has a strong link to security vulnerabilities. And we can actually see that the problematic code quality has a very strong link to defects as well. So what we see here is that red code has on average 15 times more defects than green code. 15 times more defects. What does that mean to a business? Well, it all relates to the product maturity experience and the customer satisfaction, right? So there's this very direct impact on customer satisfaction with a lot of defects, but there's more to it. Because what's going to happen with all these defects in red code? Well, you know, just like in the Stephen King movies, they are going to come back. And they are going to come back in the shape of unplanned work. And unplanned work is the silent killer of all IT projects, right? So this is the work we never anticipated, and now suddenly we need to kind of squeeze it in together with the stuff that we do have on a roadmap. So unplanned work is extremely stressful. And over the years, I've worked with organizations that have 60 to 70% of all their work being unplanned. And you can imagine how stressful that must be. There's very little room for innovation. So if we could instead move our code towards the healthier side of the equation, then we would free a lot of time where we could do not only exciting new features, but we would also free a lot of time for innovation. So there's a very real benefit to a healthy code base. Now, I've been talking a lot about how it impacts the business, how it impacts the bottom line and time to market. But what does technical debt and low code quality mean to a developer? After all, if technical debt means that we waste 42% of our time, then that will only put us in more demand. That could be a good thing. I could get a higher salary maybe, right? So maybe technical debt is a good thing. Let me assure you that no developer likes technical debt. And there's a very good reason to it. In this book called Rethinking Productivity in Software Engineering, it's a really, really good book. I think it's actually free as an ebook right now. It's a collection of academic papers. And there's one paper in particular that I took a lot of inspiration from. It's a paper that studies developer happiness. Because it turns out that, first of all, there's a link between happy developers and productivity, right? We kind of heard that in the first session today as well. So developer happiness is important. But then the paper goes much, much deeper, and it looks at what actually makes developer unhappy. What makes us miserable? And there are three things that stand out. The first thing that stands out is that we developers, we strongly dislike when we are being stuck in problem solving. And given what we just learned about red code, it's very easy to see how that can happen, right? So we've probably all been there, right? You have this bug that you discuss in your daily stand-up, and you jump at the opportunity to say, yeah, I'm familiar with how that works. I can fix this. I can fix it in an hour. Then you end up in red code that you haven't come across before, and suddenly that hour turns into 10 days, right? And that in turn is going to put a lot of time pressure, not only on you, but on the organization as a whole, due to the unpredictability of red code. And finally, in this research, there's this absolutely wonderful quote that we developers, we strongly dislike bad code that could have been avoided in the first place. And that's almost like the textbook definition of technical debt that is being left unmanaged. Now, with that covered, what I wanted to do is to present some use cases to you, because theory is one thing, but how do you take all these numbers and put them into practice? The way I've been working with my clients over the years is that, first of all, I have found that there's a lot of value in just visualizing your code health, visualizing your code quality. Because code quality, as we have seen, will constrain a business. Right? If we have a green code base, we can do very different things compared to a red code base. Now, what I think is so important with visualizations is that they allow everyone, all stakeholders on a project, not only engineering, but also product people and the business manager, to share the same understanding of what a code base looks like. And if we manage to achieve that, to have that shared situational awareness, then we're in a very, very good position to actually fight hyperbolic discounting. Because the way you address hyperbolic discounting is by priming all decision makers to think about the future, right? So the moment we are aware of where our strong and weak parts are in the code base, then we will also start to think about, okay, how can we mitigate that risk? So this is a very first step towards improvements. Finally, what I like the most about doing this research is that finally we can have refactorings come with the business expectation. And I think that's really, really important, because if we need to do larger improvements, maybe we need to redesign our problematic module. What we can do now is that we can actually say that if we do this, then we can promise that we will get very close to twice as quick with implementing new features in that part of the code. We will significantly reduce the number of defects, and we can prove that by real research. And I think that's a big, big win. Now, there's one last thing I want to talk about, and that is to keep my original promise when we talked about core CLR. How do you prioritize technical debt if you have a lot of red code? Where do you start? Is all code equally important? So let's do a dramatic case study here. So we're back to visualizing the code health of core CLR, the Microsoft code base. And remember that what you see on screen here is 8 million lines of code. That's a lot of code, isn't it? Right? Does anyone have a code base that's even larger? No, not so many of you. Just for context, the Linux kernel, which is probably the world's largest open source system, is roughly 18 million lines of code, right? So this is like almost half of that. We also see there's a lot of red code. That red code probably makes up 2 million lines. And it's red code that looks like this. So imagine having 2 million lines of code that looks like this. I'm well aware that not all of you are programmers. Most of you are probably not C++ programmers either. I used to do C++. I was a C++ programmer for 10 years. And yes, I know what you're thinking. Those are 10 years I'll never get back. And that might be true, but what I mean by that is that I have a lot of empathy with the person that's tasked with cleaning up this stuff. It's going to be really challenging. And how do we approach it? I mean, 2 million lines of code like this, we cannot fix all of it at once, right? Because just like we have to make sure that technical debt do receive attention, that it doesn't go unmitigated, we also have to balance the other side. We need to continue to deliver features. We need to continue to keep our product alive. Most organizations simply cannot afford to completely halt their feature development for 2 years, right? And just refactor code. If you did that, you would probably be out of business. You would be Netscape, right? We don't want that. So how do we find this balance? One technique I've been using over the past decade is something I call hotspots. So hotspots is something called a behavioral code analysis technique, meaning that we focus not so much on the source code, but on the actual behavior of the development organization. And hotspots is something that you can use to prioritize technical debt. So here's how it works. It's the same visualization as we looked at before, only now the colors carry a different meaning. So the colors reflect the amount of development activity. And this is data that we can get by pulling out information from our version control system, pulling data out of Git. We simply look at where have the development organization done most commit in the recent time period. And we use color to visualize that. So the more red something is, the higher the amount of development activity. It's a development hotspot. And hotspots are wonderful at prioritizing technical debt because they actually send a positive message. Hotspots are the reason why you don't have to fix all your technical debt. So please have a look at this graph. It might be the most important one I'm showing you today. What this graph shows you is a different view of core CLR. On the x-axis, you have each file in that system, and those files are sorted according to a change frequency. How often have the developers made a change to them? And the number of changes is what you see on the y-axis. Now, as you see here, most of the code is in the long tail, meaning it's code that's rarely, if ever, touched. So this is the part of the code where most organizations can and do live safely with technical debt, because it's low interest debt, right? You want to be aware of it because it could be a future risk, but right now it's more or less a free loan. On the other hand, most development activity is in a very small part of the code base at the head of the curve. And this is the area where even a minor amount of technical debt, or even a minor amount of code quality issues can quickly become really, really expensive because the development activity acts like the interest on that debt. So what Hotspots do is that they identify the head of the curve, and you can then inspect that for technical debt and code quality problems. And if you focus on paying down the technical debt in the hotspots, you can achieve pretty significant benefits with a minimal investment. So going back to Core CLR, to the visualization, we see the pattern visualized in a different way. We see that most of the code is actually stable. So this is low interest technical debt. We also see that the hotspots make up a pretty small percent of that code base. I think it's like 2% of the total code. So this is the code where I would start to pay down any technical debt. Over the past 25 years that I've been working with software development, I had so many people telling me, no, we don't have time for that. We don't have time to refactor. We don't have time to do a proper design. We don't have time to automate tests. And there seems to be this perception that there is some kind of trade-off between speed and quality. But what our data suggests here from the Code Red paper is that there is no such trade-off. In fact, the data suggests that the opposite seems to be true. In order to go fast, we also need to go well. So not only can you have both speed and quality, you actually need to have both. And what I've shown you today is how you can actually quantify, visualize, and measure code quality. And I also introduce hotspots which help you make that data actionable to actively pay down the technical debt that impacts you the most and puts your business at risk. And if you want to read more about this, I have a white paper that summarizes the research findings. You can, of course, also look at the formal white paper, the Code Red paper. If you want to dig much, much deeper into this, then I have a whole book called Software Design X-Rays that covers hotspots, different analyses for teams, all that stuff. It's available from the pragmatic programmers. And finally, the tool I've been using for the research and for the visualizations is CodeSyn. I'm going to do a demo of CodeSyn later this afternoon at 4:30. So if you're interested, I really hope to see you there. If you want to try it out on your own code, then you can try it for free at codesyn.com. And for now, before I leave time for questions, I really like to take this opportunity and say thanks a lot for listening to me, and may the code be with you. Thank you.
May the code be with you. Adam, thank you so much. Let's take some questions if we have any questions from our audience here. Yes, I'm going to run down there and give you a microphone so we can do this properly this time. Where are we? See if I can pass a microphone in that direction. Folks, just pass that along.
I hate how I sound on the mic, but anyway, I'll do that. One question on the graphics that you were showing us, the one that you referred to as the most technical one. Was idle time in there?
No, we didn't account for idle time. I mean, if you did, so you're referring to basically I would calculate the time in development, right?
Yeah,
so
especially between the commits, when you said like someone commits and then commits again, especially there.
Yeah, no, we didn't. So the thing is that if you had a lot of work in progress and a lot of work in parallel, then you would be context switching and you would have idle time, but that's like part of the general waste. So what we did was that we calculated the cycle time and we ignored any kind of idle time. We did account for some common scenarios that as a developer you start to work on a task, you get something more urgent, so you kind of pull it back into the backlog. We did account for stuff like that. And in general, there's safety in numbers. So we made sure to have a really, really massive data set across a very diverse set of companies. So we had the companies from all kind of industry segments like retailing, automation, car industry, everything, because that kind of protects you a little bit from these biases.
Yeah, I would even, sorry, I'll give the mic. I would even expect that if you would account for idle time, people wouldn't like working on red code. So it would even be like, oh, do I have to work on that? And then it would even make it a bit bigger, the difference. That's why I was asking.
Yeah. So we're actually planning a follow-up study on the Code Red paper. One thing I'm particularly interested in is how experience plays a role. Because I've seen that and in so many of the companies I worked with, that you have this piece of code that only one person understands, right? That person can safely make any changes to it. They are like the superhero. And I like to think that a lot of that unpredictability comes when we come across red code that we didn't write ourselves. So I think there's an extreme onboarding cost to code quality as well.
I'll take one more question before I send you all away. Do we have... There we go, in the front. Yanis.
Thank you. Great work and great presentation. I'm really...
Thank you. Thank you so much.
Awesome. Did you try to communicate the results of your work to the higher management of those large corporations? Because to me, this is the essence of the work. Communicating those business because these are actually business findings. Did you communicate this to the higher management, and what was their response if you did?
Yeah, that's one of my purposes because, you know, I've been a software developer for so long. This has been one of my main pain points throughout my career, that we as engineers, we very often know that something doesn't work out, and now we need to communicate it to business. So this has been one of my main drivers for doing this. And yes, I did get to communicate it to not only the engineering organization, but to the management level, to the C-level, with several of those companies involved in the study and a couple of others. And I actually think that to many C-level managers, this is an eye-opener, because they are well aware of technical debt in general. They know it's a big problem for industry, but it's so easy to ignore it because you cannot see it, right? So the moment you make it specific and say that, okay, this is what it looks like for your organization, then it suddenly becomes actionable. So I like to think that this type of data, it empowers the whole organization. As executives, we can get insights into something as deeply technical as code, right? Without having to learn to code. And as engineers, we can finally make our much needed business case for getting priorities where they should be to build a sustainable code base. So I understand I'm the only thing standing between you and your lunch, right? I don't want to do that, but please catch me during the break if you want to discuss this more. And thank you so much for everything.
Thank you, Adam. All right, folks, before you go to lunch,